our final speaker of today's session, Pawel Grzegrzolka, who will be telling us about asymptotic dimension of fuzzy metric spaces. Take it away.
Thank you for the introduction. Hello, everyone. My name is Pawel Grzegrzolka. I will be talking about asymptotic dimension of fuzzy metric spaces today. First, I wanted to thank the organizers for organizing this conference. And yeah, I know this is the last talk of the day, so we will focus on the basics today. So what is asymptotic dimension of fuzzy metric spaces? It combines two areas of mathematics. Asymptotic dimension comes from coarse topology, and fuzzy metric spaces come from fuzzy logic or fuzzy set theory. So we will first focus on explaining briefly what coarse topology is and what asymptotic dimension is. Then we will move on to explaining what fuzzy logic is and fuzzy set theory. And at the end, we'll see how these two things combine into asymptotic dimension of fuzzy metric spaces. Just to give you a brief history of these two concepts, I wanted to let you know that coarse topology has its origins in Mostel's work on rigidity around 1968, and Schwarz, Milnor, and Wolf's work on growth of groups around 1955 and 1968. And fuzzy logic and fuzzy set theory traditionally has been believed to has its origins in the work of Zadeh in 1965. That's when his paper about fuzzy sets came out. So let's focus first on coarse topology and what coarse topology really is. Some of you might be already familiar with it. But just to briefly introduce everyone to the topic, coarse topology is a branch of mathematics investigating large-scale properties of spaces. And the easiest way to understand what large-scale property really is to first persuade you that when you were doing point set topology as graduate students, you were doing you were interested in small-scale properties of spaces. So there is one of these very famous exercises you do when you take point set topology class is when you are given a metric space and you're considering a topology of that metric space, and then you're supposed to prove that if you define a new metric, you will call it d prime, and define this new metric d prime by taking the minimum of the original distance and 1, then the exercise is to show that that new topology, that new metric, induces exactly same topology as the original metric d. This should persuade you that topologies really care only about small distances because this new metric d prime doesn't have anything further away from each other than unit 1, but still induces the same topology. In other words, topologies ignore large distances. So large-scale topology or large-scale geometry will be looking at the more information that is given by the metric so that we don't ignore those large distances given by the metric. A good example of seeing how small-scale topology and large-scale geometry differ is to take a look at real line and integers. Clearly, from the point set point of view, point set topology point of view, the real line and the integers are very different. They're definitely not homeomorphic. For example, integers are totally disconnected. So from the small-scale point of view, you would say that these two spaces are not the same, not homeomorphic. However, from the large-scale point of view, they could be seen as being the same, whatever that should mean. So for example, if we take a look at integers and we think about looking at integers from far away, we see that the integers more or less have some properties similar to the real line. They look more or less the same from far away. So we can say that from the large-scale point of view, maybe real line and integers should be considered the same. And we say that if from the large-scale point of view, two spaces are the same, we say that these two spaces are coarsely equivalent. So for small-scale topology, we have the notion of homeomorphism, and for large-scale geometry, we have the equivalent of homeomorphism, which we will call coarse equivalency. And there are many other similar translations of small-scale properties to large-scale properties. We just discussed homeomorphisms, and that the equivalent, the large-scale world equivalent of homeomorphism is what we call coarse equivalence. We will not exactly discuss what these definitions are, but I want you to be aware of the fact that small-scale properties that you're familiar with from your point set topology classes, such as homeomorphism, neighborhoods, uniform spaces, proximity spaces, and the Lebesgue covering dimension, have their equivalent notions in the large-scale world, and we call them by they are called coarse equivalences, asymptotic neighborhoods, coarse spaces, or large-scale spaces, coarse proximity spaces, and finally asymptotic dimension. Covering dimension was briefly mentioned in the talk of Atish Mitra this morning, and also asymptotic dimension was also mentioned. We will focus here on this asymptotic dimension. I will show you the definition of asymptotic dimension, as we will need it to understand the asymptotic dimension of fuzzy metric spaces. If you have seen asymptotic dimension before, you know that there are many multiple ways to define asymptotic dimension. There are equivalent definitions of asymptotic dimension. I will show you just one that uses disjoint families or colors. We say, given a metric space, XD, we say that asymptotic dimension of that metric space does not exceed n, and you write that asymptotic dimension is smaller or equal n, provided that for every distance r bigger than 0, there exist r disjoint families, u naught, all the way up to un. So we have n plus 1 colors, you can call them colors, of subsets of X, such that the union of them is a uniformly bounded cover of the metric space. And at first sight, you might need a minute to digest this definition. Since we have only 20 minutes, let's take a look at a quick picture and let's take a look at the real line. By looking at this picture, you can see that we can probably cover the real line with two colors. And you can probably imagine that we can make any two sets of the same color being as far from each other as we want. So for any distance, we can make any two green sets being R disjoint and any blue sets being R disjoint 2. And all of those green sets and all of those blue sets are also uniformly bounded. So we have two families, or we have two colors, which means that the asymptotic dimension of the real line should be smaller or equal than 1, because we use the two colors, and it can be easily shown that it cannot be 0. So the asymptotic dimension of the real line must be 1. This should also persuade you that if you remember from points at topology, if you have two spaces that are homeomorphic, their covering dimension is the same. A similar idea should work for large-scale world. So if two spaces are coarsely equivalent, their asymptotic dimension should be the same. So in fact, we already said that from far away, the real line and integers are the same. So we can say that real line and integers are coarsely equivalent, which means that their asymptotic dimension should be the same. And if you just take a look at the picture, it seems like we can use the same strategy of the proof to show that the asymptotic dimension of the integers is also 1. Okay, so this is just trying to persuade you that real line and integers are really have the same asymptotic dimension. Okay, so this is all we need to know for now from the course topology, and we already know what asymptotic dimension is. So now, introduction to fuzzy set theory. This is a very interesting subject. There are multiple journals just devoted to fuzzy set theory. Its origin is very interesting. So Zadek made the observation that given a set X and a subset A of X and some point, there are only two options usually. That point either belongs to the set A or it doesn't belong to the set A. So by using this fact, we can characterize any subset of a set X by its characteristic function. So we can say that this characteristic function takes the value of 1 whenever X belongs to A and takes the value of 0 whenever X doesn't belong to A. In other words, this characteristic function is a function from the set X to the set consisting of just two elements, 0 and 1. And that is the set. And then Zadek decided to extend this notion, and he defined a fuzzy set to be a function not from X to the 2-point set 0, 1, but from X to the interval from 0 to 1. He did it to account for uncertainty of measurements, or uncertainty of the notion of belonging to a certain set. For example, if you would like to decide if someone's eyes are blue or not, you might say that you're only 70% sure that they are blue, and the 30% you're not exactly sure. So you wouldn't assign it number 1 because it's not fully blue. You wouldn't assign it number 0 because they are not blue, but you would assign it a number 0.7, for example. So this extended this notion of belonging, this fuzzy set function. So now fuzzy metric spaces should also somehow account for uncertainty of measurements. So for how do they do it? Well, for metric spaces, we take 2 points and we say, well, the distance between these 2 points is 7. Well, that's we are very sure that something happens whenever we have metric spaces, right? We say, oh, the distance, if I give you 2 points, you can always tell me the distance. But in real life, it's quite hard to determine the distance between any 2 points. And we are more likely to say that if I give you 2 points and I give you number 7, you can say, well, I am 80% certain that the distance between these 2 points is smaller than 7. So that's what fuzzy metric spaces are doing. While metrics are denoted by the small letter d usually, fuzzy metric spaces are usually denoted by the letter m, or fuzzy metrics are denoted by the metric m. So this notation mxyt, being some number equals some number between 0 and 1, means that the degree of certainty that the distance between x and y is smaller than t is 1/2. So this is this generalization of a metric space. So it gives you always have this parameter t. So whenever I'm asking you the distance between x and y, I'm asking you for the degree of certainty that the distance between x and y is smaller than a certain number t. And the same way as metric spaces have certain axioms, or metrics have certain axioms that must be satisfied, three axioms that metrics must satisfy. The same thing happens to this function m, this fuzzy metric. It must satisfy certain axioms. There are 5 of them. I didn't want to write them all down because I didn't want to bore you with details. If you would like, you can take a look at the paper called Asymptotic Dimension of Fuzzy Metric Spaces, exactly the same as the title of this talk, and all the details are there. But one axiom that I would like to share with you is the triangle inequality, that the most interesting axiom of a metric space, of a metric, and similarly of a fuzzy metric. This star on the left side, you can think about it as a multiplication. It is a continuous t-norm, but the simplest example of a continuous t-norm is multiplication. So you can think about that star on the left side as a multiplication. So this triangle inequality is defined in the following way, that mxyt times myzt must be smaller or equal than mxzt plus s. Okay, so now we know more or less what fuzzy metrics are, and then we would like to find some connections between. You can be interested in what are the connections between metric spaces and fuzzy metric spaces. Is it true that any metric space induces a fuzzy metric space? Well, that is indeed true. If you start with a metric space and then you can define a fuzzy metric space given by m of xyt equals t over t plus the distance between x and y. And this is a canonical way to induce a fuzzy metric given a metric space. And by canonical, I mean everyone does it. And this fuzzy metric space induced by a metric space is called a standard fuzzy metric space induced by the metric t. Let me just check how much time I have left. Okay, great, 7 minutes. So now our definition of now we can try to combine these two things. So we know what asymptotic dimension is. So I just put this on the slide again. So that was our old definition of asymptotic dimension for metric spaces. So now I will try to show you that I will show you a similar definition of asymptotic dimension for fuzzy metric spaces. The problem is that we would have to define what it means to be R disjoint, right? We know what it means for metric spaces for 2 sets to be R disjoint. Well, for fuzzy metric spaces, we would have to define what it means for 2 sets are R disjoint. In fact, it doesn't really make sense to say that 2 sets are R disjoint, because while metric spaces take 1 parameter, which is just distance, fuzzy metric spaces take 2 parameters, namely, they take the distance and they take the degree of certainty. So that means for fuzzy metric spaces, we won't have R disjoint families, but we will have R, T disjoint families. And we would have to define what that means, but that is really not too bad. Similarly, when we have uniformly bounded cover of a metric space, we also would have to define what it means to have a uniformly bounded cover of a fuzzy metric space. So without going into details what exactly those are, we can write down the definition of asymptotic dimension of a fuzzy metric space, and it's almost exactly the same. The only things that change from the metric case is that instead of having R disjoint families, we have RT disjoint families, And that's about it. The original definition of asymptotic dimension for metric spaces was that for every R, and now in the definition of asymptotic dimension for fuzzy metric spaces, we have for every R and T. So because we now have two parameters. So now the question is, how do these two relate to each other? So let me move on to that. So there's the definition of the asymptotic dimension of fuzzy metric space one more time. And there is a question that you could ask. If you have a metric space, let me delete it for a second. If you have a metric space, that metric space induces a fuzzy metric space. Well, what do the asymptotic dimensions agree? That should be indeed the case. Well, and it is the case. So there is one can show that the asymptotic dimension of a metric space agrees with the asymptotic dimension of the induced fuzzy metric space that we call standard fuzzy metric space. So this is a result that we would like to have, and we do have it. So the asymptotic dimensions agree whenever the metric space induces the fuzzy metric space. I should also point out that not all fuzzy metric spaces are induced by some metric space. So there are fuzzy metric spaces that are not induced by any metric. So I just wanted to make sure that it's clear that we are not just redoing something that has already been done, because otherwise we will not get any new results. As I said at the beginning of this talk, there are multiple definitions for asymptotic dimension of metric spaces. I used the definition that used the colors, so the disjoint families of sets. However, for metric spaces, there are many other equivalent definitions. For fuzzy metric spaces, it's not exactly clear if those other definitions are equivalent to the definition given by the disjoint families of subsets. It can be shown that the definition that we gave is implies the conditions here listed as number 1, 2, and 3. However, it is not exactly sure, it is not exactly clear if those conditions 1, 2, and 3 are equivalent to our original definition of an asymptotic dimension of a fuzzy metric space. So if you are interested in looking for something to do, this would be one thing that you could try to prove, that any of those conditions 1, 2, or 3 implies the asymptotic that the asymptotic dimension of a fuzzy metric space is smaller or equal than n. Okay, and for asymptotic dimension, we said that two coarsely equivalent metric spaces have the same asymptotic dimension. Well, the same thing happens for fuzzy metric spaces. If you have one fuzzy metric space and another fuzzy metric space, you can define what it means for both of them to be coarsely equivalent. And if two fuzzy metric spaces are coarsely equivalent, their asymptotic dimension are equal. Okay, and in the last 2 minutes, I wanted to show you a few examples. These are actually quite fun to calculate, but we will. They also usually agree with the metric case, so let us do that. We know that if we have a bounded metric space, then the asymptotic dimension is 0. Similarly, for fuzzy metric spaces, given a bounded fuzzy metric space, then asymptotic dimension is also 0. Since asymptotic dimension of a metric space agrees with the induced standard fuzzy metric space, it is also clear that Rn and Zn must have asymptotic dimension n when thought of as fuzzy metric spaces. One more example I wanted to include here, maybe without going too much into details. Take a look at the fuzzy metric M1, defined in the middle of this slide, and fuzzy metric M2. Both of these are very interesting because it can be shown that neither M1 nor M2 are induced by any metric. So these are fuzzy metric spaces that are not induced by any metric space, that are not standard fuzzy metric spaces for any metric space. And calculating asymptotic dimension for these two spaces is quite fun. It turns out that the asymptotic dimension of the first fuzzy metric space, M1, is 0, and the asymptotic dimension of M2 is 1. And the final result of today I wanted to share with you, it is true for metric spaces that non-Archimedean metric spaces have asymptotic dimension 0. Similarly, non-Archimedean fuzzy metric spaces have asymptotic dimension 0 if we define the continuous T norm to not be the multiplication, but we instead define the continuous T norm to be the minimum of A and B. This is quite recently, someone also published a new paper. It's on arXiv currently, that extends this notion of asymptotic dimension of fuzzy metric spaces. And they are studying property A of fuzzy metric spaces, and when fuzzy metric spaces can be embedded into a Hilbert space. I haven't had the chance to take a look at the paper yet, but it looks very promising, and I will definitely take a look at it soon. If you're interested, I can send you a link to the paper after the talk. Thank you very much, and yeah.
Let's thank our speaker. Wonderful. Thank you so much. Any questions for Pawel? When you use for the uniformly bounded covers, are you using the like metric D or the fuzzy metric, or does it not really matter?
So I am using the fuzzy metric because whenever we are doing the fuzzy metric spaces, there is no metric. So the only way we can define something to be bounded is by using the fuzzy metric and not the metric. So it's the entire definition of uniformly bounded or RT disjoint does not require to have any metric on a given space.